Welcome back. In this lecture, we will look at certain qualitative mechanisms underlying nuclear fission and rationalize why there is an activation barrier in nuclear fission. Schematically, one may imagine fission to occur in this manner. First, the target nuclei is irradiated with neutron. This gets the target nuclei to an excited state because it's neutron rich. So this de-excitation may be removed via different means. Let's say by gamma decay, that's also possible. If you have a beta decay, uh, you may have an increased atomic number. Other pathway, which we are interested in, is in fission. So it becomes increasingly non-spherical. There may even be a finite lifetime to this shape. It may be metastable without going into this state or this state, or it may proceed further and get into two separate fragments. So, based on certain spectroscopic properties, it is possible to estimate the lifetime of all these species and the time scales involved in these transitions. So, typically, you have two fission fragments, not more, but rarely you may also see ternary fragments. Then, once you get there, there can be few other de-excitation steps. There can be a neutron release, then a gamma photon can also be released. They may be these fragment itself might be radioactive, and they may eventually, after decay via gamma release or beta decay, they may end up as a stable product. After that, there may not be any radioactive decay process. So all these things is qualitative. Let's see what can be quantified using simple models. So the issue we will take up is the fission barrier. So like in a chemical reaction, when you go from a reactant to product, even when you have an exothermic reaction, there is an intermediate state which has higher potential energy. In the chemical reaction, this is referred to as transition state, but similar notion is applicable here too. So this intermediate structure in between reactant and product has greater potential energy. So for reaction to proceed, it is important to get over this higher potential energy intermediate structure. So it is possible to estimate the fission barrier. It is of the order of 5.6 MeV for U-235. So when you add a thermal neutron to U-235, it goes into an excited state. The excited state's energy is about 6.5 MeV with respect to U-235. So this excitation function, this excitation energy is more than the activation barrier. Therefore, fission is possible. In general, it is seen that greater the z squared by a, greater this number, lower is the barrier. Okay, so it is, if this is greater, the barrier height is lesser. So one way to look at the estimate the fission barrier is via exposing the nucleus to high energy photons. So uh, you can have hard photons, high energy photons. Via a photon also you can initiate fission that helps you in estimating the activation barrier. Whenever there is a barrier, supposing this is the overall energy variation, whenever there is a barrier, it is possible to decompose this overall curve to two different curves, which are monotonously changing in opposite direction. So here this overall curve can be decomposed into two different curves. The sum of these two curves is this curve. This is monotonously increasing. This corresponds to surface energy. Recall these definitions based on the liquid drop model. This is the Coulomb energy. The Coulomb energy monotonously decreases, the surface energy monotonously increases. Combination of this gives rise to an activation barrier and the net potential energy surface. So what are we plotting this against? On the y-axis, we have the energy. Here, this is indicative of certain deformation parameter. So as alpha 2 increases, you go from a spherical nucleus to non-spherical nucleus, and you get to two different fragments. So again, this schematically illustrated here. Okay, so you have the transition state. Remember, the transition state is not a minima or a maxima. It is rather a saddle point. What is a saddle point? So a transition state is a maxima along one direction and a minima in every orthogonal direction. I mean, if you've been exposed to chemical kinetics or chemical dynamics or chemical reaction engineering, you are probably aware of all these definition. So here we are plotting the potential energy versus some reaction coordinate. In this, the reaction coordinate is indicative of, or it corresponds to fission, right? So it goes from a spherical nucleus to a deformed nucleus, and you have two different fragments. So this is a point where these two different fragments separate out. That is called a scission point. Scission means to cut. So this energy difference, that is the energy of the transition state from the ground state, is the activation barrier. It gives you the barrier height. So it is possible to have a simple theory based on alpha 2. Alpha 2 is the reaction coordinate that is indicated here. So it is also called the deformation parameter. So what are we representing here? As the nucleus deforms from a spherical structure to a non-spherical structure, the surface energy increases because the surface area increases. So this is indicative of the surface energy of the spherical nucleus. As deformation parameter changes, this is a positive quantity, it's a square. Okay, so this has to be a positive quantity. The surface energy increases. As opposed to that, the Coulomb energy comes down. This is the Coulomb energy of the spherical nucleus. This is a negative term. Therefore, the Coulomb energy of the nucleus decreases. Sum of these two is what is going to give rise to that barrier height. Via certain relationship, some of which we have seen in some earlier lectures, we can estimate ES naught, that is the energy of the spherical nucleus, that is dependent upon the atomic mass and the atomic number. So this gives you an expression for ES naught. Likewise, you can also estimate EC naught. Again, it depends upon Z and A. We're not going to these derivations, but we want to just get an idea on how to express the fission barrier. So delta ES refers to change in the surface energy as the nucleus goes from a spherical shape to a non-spherical shape. So this is the increase in surface energy. Likewise, this is a decrease in Coulomb energy. So this is a decrease in quantity. This is a negative number. This is a positive number. So where a balance of these two quantities is going to give you the barrier height. When the nucleus fragments into two subcomponents, two fragments, the balance provides the barrier height. So this ratio is expressed as fissility parameter. It gives you the tendency of the nucleus to uh, for the nucleus to be susceptible to fission. So just putting all these things together, you can get an expression for fissility parameter. It depends upon the main point here is it depends upon z squared by a. So this is the expression we are after because this gives you an idea wherein fission is more possible. If chi is less than 1, uh, nucleus is stable against small distortion. How are we visualizing? There's a spherical nucleus. It is sort of, there are fluctuation from spherical shape. But if chi is less than 1, the non-spherical fluctuation dies down and the nucleus reverts back to a spherical shape. In contrast to that, if chi is greater than 1, the nuclear has no barrier for spontaneous fission. This is useful because it gives you an idea of when chi is greater than 1. When this parameter is greater than 50, chi becomes greater than 1. This occurs when Z is equal to 115. That is, atomic number is 115. Atomic mass is 265. So this is an important bound because it gives you an idea of what is the largest nucleus that can exist naturally or it can be made artificially. So even if you make an atomic nuclei with this atomic mass and atomic number, it will not be stable. It will spontaneously decompose into two different fragments. It is susceptible to spontaneous fission. So you cannot endlessly increase atomic number, extend the periodic table. So this gives you an important bound on what is the largest atomic number, atomic mass that is possible. It is also shown via more detailed theory that we're not going into this theory, but it is elaborated in this famous book. There is a ground state, which is the nucleus. While the nucleus undergoes fission, there is an isomer that is formed. This isomer can de-excite via gamma emission and can revert back to this side also. Okay, but so this is a non-spherical structure. This is spherical structure. This is the lowest energy structure. So there is an activation barrier to go to this. So there is a finite lifetime. It can either go here or it can come tunnel through this and undergo fission. This pathway is called isomeric fission. The nucleus can also undergo spontaneous fission without this local minimum. One of these two pathways are possible. This, of course, depends upon the Z and A. We won't go into this theory. It is elaborated here. In the next lecture, we will look at some additional features of nuclear fission. Thank you.